So the eigenstates have n-1 dark states, which don't have any cavity components, so I never see them by probing the cavity. And they have two potentially bright states, which are superpositions of all the atoms being excited, or sorry, each of the atoms being excited, or none of the atoms being excited and the energy all being stored in the photon. What are the energies of these bright states? I'll focus on the off-resonance case. And the energy shift, like we had before, away from the situation where there was no coupling to the cavity, would be given by this expression. So it's like what we had before, except this quantity g squared is going to be added for each of the atoms inside of the resonator. Sorry, this is not what I wanted. This is I wanted the off-resonance case. Wrong expression. So for the off-resonance case, I was just wanting to calculate the energy shift. That's going to be similar. And now I can go back and think about not just the first excited state, but all the excited states in the system. So that's also going to be proportional to the photon number. So what I have is a linear cavity situation where the presence of atoms in the cavity has shifted the cavity resonance, and the cavity resonance shifts are additive. Each of the atoms acts like a little bit of index of refraction, which shifts the cavity frequency by this amount, g squared over delta, and all of those shifts just add up. Now, how does optomechanics come in? So each of these quantities is a function of position. So I have that the cavity energy depends simultaneously on the positions of all the atoms inside of the resonator. Oh dear, that sounds really complicated. And indeed, the first experiments that looked at many atom optomechanics, or maybe the first theory papers, which said, well, we think we know what a single atom does in a cavity. Let's stick two in there and see what happens. They were terrible. I mean, they were just so frightening. There were things that the diffusion force on, the diffusion of atom 1 depended on particle 2, and it was just, atoms were dancing around willy-nilly. It was a very poorly controlled situation. So that seemed very uninviting. But it turns out that that great complexity can be simplified if you think about the atoms doing something very simple. And then we can think about what this type of frequency shift looks like in terms of relating to the atomic dynamics. So let's think of a few of these enormous simplifications. So situation one. I'm going to consider a situation where all the atoms are harmonically trapped. And they're all trapped in the same trap. And they're trapped tightly. So that, I'll tell you what that means in a minute. And I'm also going to ignore the transverse motion. So if you will, I have a cavity inside of which there's an electric field. There's the electric field. And the atoms are all going to be pinned at some location, right over there. And they're confined in a really deep trap. And the trap is so deep that atoms are not going to move from this equilibrium position by very much. So let me let each of these atoms be displaced by some small amount from the equilibrium position, and require that these displacements are always small compared to the optical rate.
Yeah. What is the harmonic potential there? So I thought it was, do you have an extra potential?
It's going to be due to another right field, but it doesn't really matter what it's from.
Okay. But this is different than what the other.
It's an additional, it's an additional track. Not provided by the probe field, just an external, classical. There's a spring attached to the atoms. So now we have a prayer. So we look at this energy shift. So the frequency shift of the cavity, which we had as g squared over delta. And this is g naught squared over delta times the sum of cosine squared kj. Because the cavity field is just periodic. And now I can go ahead and expand this expression in terms of the displacements of each of the atoms from their equilibrium position, and use this product kz, which is small, as the expansion parameter. And I obtain the following terms. So to zeroth order, I just get n, this is the number of atoms, using 0 squared over delta times cosine squared of k is 0. And then to first order, I get g0 squared over delta. Sine 2kz. And then I can get additional terms as well if I expand to higher order, but I'm not interested in doing that here. And this term is going to be what gives us contact with cavity optomechanics. How so? Let me simply, rather than talk about the displacement of each of the atoms from its equilibrium position, talk about the center of mass position. The displacement of the center of mass away from the equilibrium position. And if you will, I can quantize this. Where this is the harmonic oscillator length for the center of mass. And that will be the mechanical resonance frequency of this trap that we've drawn over here. Okay, so then I obtain that this expression over here, clearly I can substitute in the center of mass position because I have this summation which matches the summation over there. And I work it out. And I can find that the shift is going to be some frequency times the diagonal speed. So that's this optomechanical coupling strength, which I believe John was also speaking about. So that was his G naught. I use G naught to describe the single atom cavity QD interaction. So we'll just take a ON just to make sure we know what we're talking about. But this frequency here, which is now defined just in terms of atomic stuff, and plus I have to know where the atoms reside inside the cavity. That's something that's actually under my control. But it's sort of described in terms of ab initio stuff that we derive from the past lecture. And this thing then, without relying on any material properties, tells me the single phonon here I mean the center of mass excitation, the single photon coupling strength. And so I can just put in numbers for you. If I work through all the ... that I have here, I find that this quantity GOM goes like the square root of the atom number there's a square root here that cancels in an n from elsewhere, from putting this guy in. There's G naught squared over delta. This thing we know was 13 megahertz. This thing I'll have to tell you what setting I'm using in my experiment. And then there's the mechanical frequency. So that's just something I have to pick experimentally. And to make things back to have the right units, you can stick the recoil frequency up here. Just defined as follows. So just put in some numbers that match experiments that we've done. So maybe 1,000 atoms or so. We work at a tuning of maybe 10 gigahertz from resonance. We work with a trap that's about 100 kilohertz in its mechanical frequency. And I get that GOM is 2 pi times 100 kilohertz. Okay. Is that big or small? One thing we might want to compare it to is the line width. So in our present system, the ratio of these is about 1 to 20 or so. 1 to 10, 1 to 20. Typical in our stuff. We've done other experiments where we've made this number a lot bigger and this number a lot smaller. And the ratio was like 2 to 1. So we could get this G0 to be larger than kappa under those conditions. Questions?
So you can pick any mechanical frequency you want.
Yeah.
So
So we can make it softer.
100 kilohertz, why was that? I guess how did you settle on that, having all the parameters based?
100 kilohertz, that was chosen because we were trying to make sensitive measurements of the modulation that the atoms put on laser light exiting the cavity. And we were trying to escape laser noise and other wonder kind of stuff. So we went up at high frequency to get out of the forest of noise.
So the lowest frequency was reasonable magnitude?
We've also done it with 30. I could have put that number in too. We've done it with 200 kilohertz, whatever we feel like.
This depends on the potential that you apply.
This thing, yeah, which in our case is generated optically by some other beam, and so it's just controlled by the intensity of that beam. And you know, it can reasonably go up to maybe a couple of megahertz, but then maybe we start burning spots in our mirrors. In terms of time, should I stop here? Because I started about an hour ago. Should I just stick to the time?
It's up to you, yeah. I think you started at quarter till, so you have another 5 minutes in theory.
All right. Okay, let's move on. Okay, let's think of another situation where the atoms are also harmonically trapped. But the traps are all distributed throughout the cavity. So there's maybe some atoms trapped here, and there's some other atoms trapped here, maybe somewhere else. But let me still allow all these traps to have the same mechanical frequency. So this describes experiments that we've done, and also folks at MIT have done. Okay, so I'll just do what I did previously. Again, I'll define the displacements of the atoms away from their equilibrium positions. But each one has a different equilibrium position because it's in a different trap. And I write out this linear term as we had earlier, and I have to take the sign and put it into the sum. So let me define, instead of the center of mass degree of freedom, let me define a different collective variable, which is just going to be the positions of all the atoms away from equilibrium, but now weighted by this factor, which tells me how strongly coupled they are optomechanically to the cavity field. And then to normalize things so it looks like a regular normal mode variable, I'll divide this by some effective atom number, where this effective atom number is the sum of sine squared. And you find that everything follows. So it's exactly the same structure. There's a single collective variable in the atomic system. It's not a center of mass per se, it's a different collective variable. But there's a single collective mode, a single collective variable that couples to the cavity. It corresponds pretty well to a normal mode of the system because each atom is oscillating at the same frequency. And I have optomechanical coupling strengths just given by that expression over there. I just replace n by some effective atom number, which, maybe it's a half or something. It's not too far off. This collective mode that I couple to, let's consider what it looks like. Imagine I have atoms trapped in an array. And maybe the cavity probe field has a wavelength that's really large compared to this array, which is not the situation with real life, but it's easier to picture. So this would be something like the functional dependence of sine of 2k, which was to define the strength of the coupling, of the mechanical coupling. So this collective variable would be one where this atom participates strongly. This atom participates strongly, but with the opposite sign of its displacement. So the collective mode of motion that's described by all those arrows, that's the synchronized motion of all the atoms, looks kind of like a phonon does, right? If you have a crystal, if I have a crystal, and I think about long wavelength phonons and what a standing wave of such phonons looks like, it looks exactly like the concerted motion of atoms in the crystal, or nuclei of the crystal, exactly in this manner. Okay, so it looks like a phonon standing wave. With wave vectors of plus or minus. So that becomes relevant later. Let me think of another situation, which is simple to consider. I have atoms that are harmonically trapped. Maybe I have just atoms in a few harmonic traps, not a whole bunch of them. It's hard for me to keep track of. Let's say few means two. So let's say there's two harmonic traps, which contain N1 and N2 atoms, but they have different mechanical frequencies. Okay, so now I would go through the rigmarole, and I would find that it's convenient to write down the cavity frequency shift in terms of the displacement of two different mechanical oscillators. And the math would have worked out just the way it had worked out for these other situations. So if I know how to do this, if I know how to spill my atoms into two different harmonic traps, and set the frequencies of them somehow controllably different from one another, then I also have the ingredients for doing optomechanics with multiple mechanical elements. There's no problem in doing that either. So now let me show you a couple of Berkeley experiment-related slides. So the way we've done our experiments of late is using an atom chip, which I don't want you to know very much about. But suffice it to say that it allows us to do atomic physics experiments with a pretty high degree of control over the magnetic fields and the magnetic traps in our experiments. So the way this works is we gather atoms in a magneto-optical trap. We trap them magnetically. We cool them. We transport them along to this location. At this location, they're placed right above this, this hole, which we've dug through the atom chip, or through this silicon chip. And then we take two mirrors and we face them across each other, or they straddle the chip right above this hole in the chip. And so we have an optical mode that's vertical, and atoms are brought in from the side, and we can place them where we want inside of the optical mode. So that's like our cold atoms into the cavity delivery system. That's what the atom chip is. So I can place them where I want initially in the experiment. And geometrically, the way they look is they're like a thin pencil like this. So they're long in one direction, but they're really tightly trapped in the other. One of those directions is the direction along the cavity axis. Then we dispense with the magnetic trap, and we turn on a standing wave trap inside of the cavity. So we use light that resonates with the cavity, but it's detuned from the atomic resonance.
Dead switch. That works.
And so now the atoms rush into the nearby well of this lattice. So from the examples that I've been giving you, I'm considering each of these pancakes, each of these potential wells in the optical lattice, to be one of those traps. And those traps are not placed at the same locations as where, let's say, the probe field, which is at this different wavelength of 780 nanometers, where it has its brightest intensity. And the benefit of that is that depending on which initial trap I put the atoms in initially, I will have a different optomechanical coupling strength. That is, I control this parameter by putting the atom in a different initial position. So I can put the atom, let's say, at locations where the probe intensity has its sharpest gradient. That's where this quantity over there is maximized. That gives me maximal linear optomechanical coupling. Okay. And we know that that the atoms are, actually in our experiment, they don't live in a single well, they live in a few neighboring wells, although recently it's down to a single well. But it doesn't matter too much because nearby wells all have somewhat different coupling strength, but the different wells have the same mechanical frequency in this case. So now I'm realizing this example number 2 experimentally. So I can still think of the atoms as being a single mechanical element with which we're doing optomechanics. But if I want to make contact with this example number 3 and start doing experiments with optomechanics with multiple mechanical elements, I have to find a way to make the mechanical resonance frequencies of these nearby traps different from one another. So that we've been doing recently by using 2 different standing waves to form the potential that traps the atoms at 2 different wavelengths. And so the total potential that the atoms see is the sum of them. That's what this white squiggly curve is. So there's some locations in the cavity where the 2 standing waves act in concert and give me a very high mechanical resonance frequency. There's other places where they cancel each other out in terms of the mechanical resonance frequency. And there's this wide region over here where the mechanical resonance frequency varies sharply from one well to the next. So now, just like I showed you earlier, if I deposit atoms in a few neighboring wells, I have a few distinguishable mechanical oscillators to do experiments with. I have to think about the fact that they also have variable coupling. There's this factor as well. There's variable coupling to the probe field. But in any case, I can see the different mechanical frequencies if I take atoms and place them in different initial positions, shove them into the superlattice trap, and measure the mechanical resonance frequencies. I get things that I expect. And in particular, over here, there's a region where at neighboring wells, the mechanical resonance frequencies are quite different from one another. So if I just stuff atoms into a few of these wells, I can see several mechanical resonances. And now think about doing optomechanics with, in this case, let's say 6 mechanical oscillators, all of which are near the ground state of motion. Maybe here's a good place to stop. Other questions?
Thank Dan for that great talk.